everything. Is that a 1K or 2K? Oh yeah. Yeah, so these two becomes 1K, right?
Yep.
And then it's gonna be like that.
Yep.
So these two is a 2K resistor. And now you got 5 volts, 2K, 2K, and you treat everything here as a load. Keep in mind that's critical because the shape of the circuit looks really odd. So you want to treat this one and ground here. I didn't draw it. So that's a network. And everything behind it is a load. To remove the load and then do a Thevenin here.
Right. Wait, so the V3 goes to V over 2, right?
Let's start from here. So you agree with that, right? 1K, 1K, 2K.
Right.
So 2K is shorted to ground. Wait, yes. Okay. So you have, if I rotate this guy and put it here, 2K, right? 2K go to ground. Remember, agree with that?
Yeah.
Okay. And here's a network. That's a load. Whatever load there is, it's just a box. So for 7, you want to remove that one first. Okay. And that's a circuit. So what's ET or VTH? Yeah. What is RTH? You remove the load and look backwards and short it, right? So it becomes you look backwards, so the current split into 2 and merged here. So which means, yeah, 1K for RTH. So the whole thing here becomes and then connect to another 1K. Here's the final V out. I'm not moving. Oh, right now, right?
Yeah.
Yeah. So you short this one again.
Right, and those become a 2K, and then they become 1K, 5 over 4.
Mm-hmm.
And then for the other one, that just becomes.
For the other one, you short it, right? Because superposition, you just short it, and then you the 1K, 2K, 1K, 2K, so it becomes 5 over 2. And then you.
So I did all this, and then I think I got the right answer. I don't know what I missed.
What's the right answer there? Let's take a look.
I didn't bring my calculator, but it turns out, I mean, it's the same as that. This is 3 over 4 instead of 6 over 8. So this is the 6 over 8. Oh, there it is. So this is 15 over 4. Right. I just didn't see it.
Is this minus A? Is this number 3? And verified. Okay, how do we implement this in hardware? We'll do that. I got a 3-bit full adder here, for example. It's a ripple carry full adder. Which is which? Same problem, make you nervous. We're adding B2, B1, B0 to what? A2, A1, A0. I guess all of us need an intelligence test or something. Need coffee.
Go sleep for like a week and a half, and then maybe.
Which is which? Yes. All right. So it's definitely the adding operation. How do we make a subtraction from that? So the design is really interesting and smart. Not inverted, but you need to plus one as well. You have to invert it and then plus one to make it a negative number. So when you are doing addition, it's actually subtracting that number from the. Mhm. So the design is like this. XOR gate. Instead of using A here, they use this A0 here. So not here anymore. And here's the switch. 1, 0. You can change it. So if 1 XOR 1, what is that result? 0, right? They're the same. 1 XOR 0. Yeah. So what about 0 XOR 1? Okay, what did you find from these two operations? So 1, 0 is just all the digital possibilities. What if I call this A? So 0 XOR A is what? 0 XOR 1 is 1. 0 XOR 0 is 0. 0 XOR A is, yeah. Toggle, right? Mm-hmm. What did you get from this? Think about it for a second. I don't want to directly give you the answer. It's better to think about it in your mind. I can change it. Yeah. If I give a 1 to it, then all the A's are toggled. And we need to toggle it to get the 2's complement, right? If we put a 0 there, all the A's are unchanged. So A will be tunneled to here and still adding operation. So it's either sending A's here or sending A naught here. What else we're missing for 2's complement? You need to add 1. Where should we add that 1 to? So for example, we want to do a subtraction instead of addition. You want to turn the switch to where? 1. So we got a negative number, right? It's a subtraction, okay? Okay, yeah, so I flip every single bit. What else? You want to add a 1 to it. Where do I add a 1? So I'm going to pull this up to VD. Wait, no, how do you do that? You need a person sitting in the chip or standing beside the chip? Yeah. So you can do it automatically by doing that. Because whenever it's 1, it's flipping every single bit, and also that 1 is being added to the carry in. It's really neat. It just works for the logic. No, it's just works for the logic. It's not an inverter. It's not an inverting logic, right? It just works for this operation or this application by chance.
We got lucky.
You couldn't use an inverter. How do you use an inverter? Inverter is one input.
Well, then you get, well, that would be, it would only be the subtractor.
Yeah, you're always inverting A0.
Yeah.
You don't have the one there. Where's the one? You need the one.
C minus 1 to
Oh,
you couldn't do addition.
yeah. So you need another adder,
Yeah.
right? Because this one can do both, right? Oh, we did it in embedded. We forgot everything, right? Oh, reminds you. Okay. Yeah. That's longer than
you were
6.
bringing it up. I thought you were gonna look at me and be like, "You remember how we did that?"
You have 2 more stick figures embedded, so I'm not gonna take it.
Oh no.
Oh.
Coding.
Oh, good.
Verilog.
Easy.
Yeah. So is there an alternative way to do it, like a mux? I think or another design solution tool. Ah.
No, I think you used the
Multiplexer. Duh. He's showing me.
What if we want to subtract the 4? Well, because, oh, I guess you could do it.
It's just the names, right? Yeah. Mux. So you can select which one you want to put in there. Yeah, let's think about that together. What's the solution to it? Because the mux has a selection bit, right? Do you want to short them together or not? Yes. We don't have that many pins to control that many wires. So mux has 2 inputs. So I can select which one to be sent to the output. What are the 2 inputs? Yes. How do you get A2 not? Yeah.
It seems way worse.
Yeah, it's taking more space.
So why would you?
So I'll just let you know
okay.
there's an option here. So if you give S a 0, but you can swap the position, right? But if you give S a 0, you want to pick up what? Regular, yeah, the original one here, right? And if you change this one to 1, you want these ones, right? Why? Yeah, you want to add a 1 to it whenever you get a negative numbers. So what is the mux? Supposed to remember it. If you want to design it's a static logic, right? Combination logic. If you want to design a combination logic, what is the starting point? The starting point of it. So right now we just need a mux, and we know what is the mux because it's just like if I have a 0 here, it's picking up this one. If I have 1 here, it's picking up this one. That's the logic of it. I want something can do that job. Very clear. It's a very clear requirements from the customer. How to design it? How many inputs? How many outputs? What's the starting point? True stable.
Yeah.
And there are how many combinational inputs?
Maybe I should just become a businessman.
Psychology. Let's just say A and A naught. What about that? Okay. Wait, is that possible? It's just not going to happen, right? It's fine to list it there. Is that a problem? No, it's not a problem. It just won't happen. It just won't be a case. It's okay. It just won't happen in the real life. It's okay. All right, what are the Y's? Wait, so 0. So if, let's say that, if S is 0, it picks up all the A's, right? So it's going to copy A, so 0, 1, 0, 1. Do we want that? So if S is 0, do we want an A or A naught?
Wait.
Oh, wait, no.
Yeah. If S is 1, do we want an A or A naught? Yes. Right? Then what's the logic here? Just look at the ones, right? Or you can, what's the next step? Okay. I forgot the name. K.
I don't think it's Cal.
That's also.
0, 0, 1, 0, 0, 1, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 0, 1, 1, 1.
What about, yeah,
But then you do the middle two also, so you don't get
So those, the two in the middle cannot happen.
it can never happen.
Well, not with this setup, but they could in a different setup. Like if we
Well, we're
wanted to put
only
A9,
doing
if we
this
were
setup.
putting A1 and A0.
But we are designing the circuit of the max. The max can be used for any applications. It's just being used here, which doesn't have that kind of input, right? But we don't need that input. We just need something perform like a max. You can put whatever signal to the inputs. It just won't happen here. One of the entries just won't happen here, which is okay. Or how many won't happen? 2 won't happen, right? Yeah. It won't happen. Won't happen. So you're you're never getting this one, which is okay. You're just never use it, but still have the circuit perform like a normal mux. Mux is mux. Like the op amp is op amp. You just grab from the drawer, you use it. Nobody care about what signal you are putting in there. So what is Y? This is A.
That's not A naught.
That's not A.
A,
Yeah, that's not A.
A naught.
Like, you know.
A, yeah.
Yeah, A. It's just S, A naught, A.
See, it's not happening.
What? Oh, right,
A
it's,
naught, A
it's,
naught.
okay, my bad, yeah, yeah.
Oh.
S,
A naught.
A naught.
Okay.
I was in this side.
So it's very straightforward. Because whenever S is 1, this becomes 0, so this will be removed. So A naught will be passed to Y. Right? When S is 0, this will be nothing, and this one becomes A. So it's a mux. It's able to pass either one. And I'm going to introduce a different structure of the mux, since we're going to use it in the LU as well, to use the transmission gate. So you can use that latch. It looks great.
It does look a lot better than the version.
And they are very easy to draw. Just draw a box. Should I connect these two? Yes. So these are the two inputs. And if I call this one SI, and these two becomes S, and this is Y.
Wait, what's that side?
S naught.
Oh.
That's just one signal. This is one signal. This is one signal that's being inverted.
Oh.
We can add an inverter to it. I think this is what we did in LU. How this works. So when S is 1, what's going to happen? When S is 1, this is 0, right? Right?
Yeah.
And this is 1 because this is S, shorted to S. So if your PMOS has a 1, what's going to happen?
It's gonna.
PMOS is 1, this is off.
Yeah.
What about this one? 1, 0. What about this one? Both the PMOS and NMOS are on. So B, it passes B, right? When S is 0, it passes A. Same logic, just 4 transistors. If you're counting the inverter, probably 6, but the inverter has 2 transistors, only like 6 transistors. So how many transistors do we have over here? This one. You still have to count the inverter in here, right? Do you? And every AND gate has 6 transistors,
Oh, yeah.
right? The NAND gate has 4, and you have to invert it. So every AND gate has 6. So I did 6 here, 6 here, and OR gate has another 6. And we're not even counting these inverters. So it's 18 already. So this works a lot better. You know, it's a lot better than the other one. So this only has how many? Like 6 transistors, but compared to the XOR gate, how many transistors we have in there? Remember?
It was like 24 or something.
But for the but we built a AOI one. Remember? So the AOI one has less, but still more than 8, right? Still more than 8, or 8, or more than 8. So you couldn't really tell which one's better right now. This may be smaller space. Who knows? And high-speed slider, which will be the lab next week. It uses the UI logic instead of all the very long ones. And I really don't want to derive it because it's an empirical result, I think, from the textbook. I could write down the logic equations for it. You know the flyers. Really quick quiz question. What is S? It's like this, right? A, B, Ci. And the two outputs are S and Cl. Okay, what is S? That's the easier one. You gotta know that. It's common sense. Right? I'll repeat this for more times in the semester. So what is Cl?
It's
That's the logic equation for it. So is that an easy conversion to the AOI logic? Like 3 XORs, we haven't done that yet. We did 2.
Oh,
Mm-hmm. So you can move things around, you know, eventually make up this. Let me see, what's the conclusion? S equals A or B or Ci, Cl not, or ABCI, CO not equals A not or B not, and A not and B not or Ci not.
That's a high speed one.
Yeah. Why do we want to convert these two here?
Less.
It's AOI, yeah. This is not AOI, it's XOR. Mm-hmm.
Well, you can do it.
have you seen any of this? I don't think I've made one right stick diagram ever.
Turn in the homework.
Yeah, all of my stick diagrams are wrong.
The homework? You didn't do it right in the homework?
No, you can't make stick diagrams if they were right. Spent so long on that homework too. Probably the longest I've spent on the homework, and I got them all wrong.
During the day.
Oh, was that when I first did that? It was. Oh, okay, that makes sense. Even if I did though, I would have said I got the same answer.
You should have come, on Thursday and used that for supper.
Nobody told me you guys were coming on.
We always
are on that Thursday.
Always in that room.
We actually had cots set up in there, sleeping.
That's really easy.
My house got 4 quarters of living room.
We're gonna draw it.
How do we draw it?
Ventilation for the room. There's a little window there.
You can open it up and peer out of it.
I put the solder thing,
Oh, yeah.
solder vent right next to it.
You can just put the gun on for your heating.
Yeah.
Just open them.
It's already
put it there as is.
Think about it. So it's gonna be takes a lot of time. You can imagine if you add 2 bars on it and doing the De Morgan's law, right? Let's just do it and then add an inverter.
Are you allowed to put A naught or B naught? Can that become A B NAND? Like inverse.
Oh yeah, yeah.
Or does that?
But you want to separate them under the bar, even though we don't have a bar, right? But I can invert it later. But you want to separate them into individual ones instead of one with a bar on top. That interesting? I don't want to. So a lot of time we have never done that, like with a couple things under one bar. So don't do that. It probably will give you a wrong answer there. Yeah, just split it if you have multiple things under one bar. Okay, let's do the S first. So this is ABCI. These are in parallel on the top.
Yeah.
Now, are you distributing this? No. I think it's
ABCI in series.
Series with the same.
Oh. Distributing, yeah.
And then it's a beautiful line.
And then ABCI in series. Oh, that was.
Yeah.
I think if I was doing some different stages, I wouldn't be able to do it once.
You like know the basic rules.
I do, but I just don't understand. I don't know. I'm gonna have to go spend a few hours to figure that out.
I just sit there
The
and
exam had 9, so.
yeah, how do we? Also, this needs to be inverted, right? Because this is S naught, right? Doesn't have a bar on top. This must be S naught. We invert it to get S, right? It's
Do we
fine.
have to have a separate
Yeah.
inverter on the side?
Yeah, that's what I did. You may be able to, but I don't want to. I think we have time to do it. How many? 1, 2, 3.
8.
Oh, yeah, 8 diffusions.
No, it's 8.
3 in parallel. You know how to do it. Okay. And 3 in series. And 1 in parallel. Mm-hmm.
I like it.
Yeah. Let's see. So this is. Let's label it later. Okay. What about these ones? 3 in series. It's good to directly do that. So 3 in series here. And then 1 first, right? And then 2 in parallel. Oh, 3 in parallel. Right? It's a high-speed fighter.
Yeah, that's gonna be pretty easy to build.
See out. See out.
Way easier than all the XORs.
If they're the same.
C out. A naught, B naught. Wait. Did I have a different structure here? I think I used the old. I didn't use this one. Because we know that CO is this one. This is easy enough. Why do we bother, right? I think the textbook used this one is because if you plug this one here and expand it, it becomes exactly this one. That's just empirical, I think. But I think this is easier than this one. Do you agree with that?
Yeah.
Looks easier. Yeah, so we just need to do this one to make CO and invert it to make CL for S. So just feed CO naught here for S. Right? So for this one, we can have A, B, and CI. So AB, they are, oh no, this is AB, right? In parallel.
Yeah.
And CI, AB in series, and CI in parallel. And here it's going to be AB and CI. So this is what, CL or CL not? Wait, this is actually CL not, right?
Oh, okay.
Oh, yeah.
Let's do it really quick. Still have a couple minutes.
Don't you
No, we want to see out not to feed into X, because we want to see out.
Oh, okay, gotcha. So you just take
So we
that
invert it at the
out.
end and then it's just.
How to do it?
A and B parallel.
Could we just do one liner here? I didn't do a one liner on my notes actually. It might,
That is a one liner.
huh?
Isn't that a one liner?
I don't know if we can do it actually. We don't have time right now, but
I thought that meant one liner, but it was one liner.
I hope we can
So
do
one
it.
line is one line.
Well, like on the exam, I did them like that.
It's different, right? Is it different? Yeah, let's do it. I think Wednesday. No, this is Wednesday right now. Friday. Okay. No.
Make my grade.